Hi, welcome back to the Chico Statistical Lecturing Series. And we are still in this unit, expected value. And this is our second topic on expected value. We're going to talk about the moments, okay? So in this lecture, we're going to cover three things related to the expected value. So the first, we're going to introduce the new terms we call the moments. So we have two kinds of the moments. So we have the moments about the origin and the moments about the mean. Then the second thing is here we're going to talk about is the Chebyshev theory, or some people call the Chebyshev inequality. Then the last video, we're going to talk about one very important concept. We call it the moment generating functions. Okay, so it's an MGF. So the moment generating function, basically for each distribution, we can find the moment generating function. Then from the moment generating functions, we can find the mean and variance, those key statistics we are interested. Okay, so now let's start. Before we introduce the moments here, right? So the first thing is let's go ahead review what we did before here. Okay, so let's take a look at the reviews here. So the prior lecture, we talked about the expected values, right? So I think you guys still remember the way we talk about the expected value. If you remember, I used you're going to have a weekend party and the different groups of the people you're going to invite it. So we said the expected value of X, here is your random variable, is what is the value of each group times the probabilities, right? Then you add them together, right? So you add all the possible value. That's what we call this expected value of a random variable X. So the same way, if you have like this is discrete, right? So that means you can, the value of X is countable, 1, 2, 3, those things. Also, if you have the random variable, it's continuous. So the same way we say, hey, the expected value, you just use the value of your random variable, and then you times the PDF, right? So then you find the range, the domain of the X, and then you integrate that. So that's what we call this expected value. Then also in the previous lecture, we say, hey, you can also find if you have a function of your random variable. So it will be the same, instead of just use X here, right? So instead of just X here, then you replace with what? You replace with GX, right? So this will be the GX and the PX, and then you add all the X, or you can do like we said, the GX will be equal to what? The integrations, right? So like integration from your domain and then the GX, f of X, dx. So that's it. And then one of the very key things we need to know is like if you have any constant, right? So if you expect the value of the C, what is if C is a constant, what it will be C, right? It's pretty simple to prove. So for examples, right? So if you have a continuous, then that means it's C times f of X dx, right? So you put the C out, and then this is negative infinity, the f of X dx. So what is if you integrate the whole sample space here is 1, right? So that's why it's equal to C here. Okay, so that's one of the things we did, and a little bit of review about what we discussed in the previous lectures here. Okay, so we talk about today, let's talk about the moments here. Okay, the moments is just like another way to talk about the expected value here. So the moments, so the things a lot of students get confused is the notations here, right? So like the notation sometimes a little bit confusing here. So we have two kinds of the moments here. One of the moments is it's the moments about the origin. And then the other ones here, this is a moment about the mean here. Okay, so what is the moment here? So this is, let's take a look, the moment about the origins here, right? So the moment about the origin, that means really you just find the expected value of XR. So these notations here, these notations, okay, so just be careful about the notation. This is, we call this is the R's moment about what? The origin. We know the origin is zeros, right? So that means in here you will see x minus 0 to the r's power. Then from the previous lecture, we know what is the definitions here. The definition will just be what? The xr and the px or the f of x, right? So in here, it will just be the px or the f of x, doesn't matter. So if this is discrete, right? So then you add all the r's here. That's what we call the yeast. So this is for the discrete. Then for the continuous, so the continuous is just you integrate, right? So the same things, right? So now your function, like here, the gx is what? Is xr, f of x dx is here. Okay, so here, this is where is the confusing part. So the moments of the origin, we use these notations here. It's kind of like the mean concept. So it's the expected of XR. The notation we say this is the mu to the R's moment, right? So this is R's moment. And then because to the origin, I use a prime here. Okay, so I use prime here, except when the r equal to 1, that means I'm finding the ex, right? So the expected value of x, just like we talked about in the previous lecture, we say this is kind of like long-term averages, right? So this one, expected value of x, if you according to this notation, should be u1 primes, right? But in general, we just use u, right, to represent the mean. Okay, so represent the mean of your random variables here. So this is where is get a little bit confusing here, right? So this is the, we call this the moment about the, the origins here. So now let's take a look here, right? How about if I have the moment about the mean? That means we write in these notations here, this is x minus what is the mean here. So this is what we call is the means here, right? So this is x minus mu to the what? The r's power. So this is what we call, okay, so be careful here. This is the r, this is the x minus mu, right? So this is what we call the r's moment about the what? About the means here. Okay, so the notation we use this notation. We say this is u to the what? U to the r's here, all right? So this is what we use, this we call this u to the r's here. So do not get confused about that. So the same things here. So then after you know the definition, right? So the expected value of x minus mu to the r's power, and it will just be either is discrete, you just x minus mu to the r, then the px, you summarize all the x over, you integrate, right? If this is a continuous random variable, the f of x dx here. Okay, so that's it about the first things we talk about is the, the two definitions here, moments about the origin and moments about the means here. So like I said, this is the notations, right? So moment about the, the origins here, right? So you use this, you have a prime here, right? But the only difference is here is when r equal to 1, instead of say u1 prime, we just put it u, because this is general in statistics, we know we call it the mean. And then the next thing is here, the moment about the means here, right? So moment about the mean will just be e the x minus mu to the r's power. The notation we use is mu r. Okay, so let's see the review and the definition. As I said, a lot of students, they got confused. It's because this is prime, no prime, and so that's what is kind of a little bit of confusing here. Okay, so now let's take a look. This is my former definitions, right? So if so that's why we said this is R's moment about the origins, right? So that's how do we do that? And then this is how do we use the notation, right? It's the primes here. So then this is a special definition. We say the mu1 prime is called the mean of the distribution, or simply the mean of the x's. So we typically don't put any prime, don't put any indices there. Okay, so then the next things we talk about is the moment about the means here. So the r's moment we called is the x minus mu to the r's powers, right? So this is, we don't have the primes here. So this is, we use ur depends on the discrete or continuous. Is it clear? Okay, so now let's take a look. Okay, so some special one. So the first one, the means about the origin. This is the special one, right? So it's the first, this is, we call this the mean of the distribution, right? So it's the first moment, right? So this is the first moment, right? So it's the mean, right? So this is the first moment. So this is the fourth moment. That's why we call this the means here. Okay, let's take a look, all right? So the next one here is very important. So this is, we call it is the variances here, okay? So the variances is just what? So here, look here. So variances here is the mu2. So variance is what moment? This is our second moment, right? So this is the second moment about mean here. Okay, so the second moment about the mean, and sometimes we call it variances. So you will see these notations here. You will see like sigma, sometimes you put a sigma x, or you put a variance x, or you put a vx here. And if you take the square roots of it, it will become the standard deviation of x. So what is the second moment? So I put a graph here to show you that's what is the sigma mean. The sigma really means is how wide is your distribution spread. All right, so like in these four graphs here, if you take a look, right? So they are all have the mean equal to 5. That means like the center is all 5s here, right? But obviously, these four distributions have a very different shapes here. So the first ones here, you can see, the way they spread it out is kind of like the spread far. So that's why you have a far high variance. Then when the distribution get tighter and tighter, so you see the variances here. Then like this one's here, majority of the variations is like in these areas, right? Because it's very concentrated. So the variance is getting smaller and smaller. So as you see here, right? So the biggest the variances here, that means they spread out. And then the smaller the variance, that means majority of the value, they are clustered in certain areas. Okay, and now in here, the next things here, this is one very, very important series here. So that means the sigma square, that means the second moment of the mean will be equal to what? Second moment of the origin minus the first moment square. Okay, and So this one's here, if your professor or your teacher wants you to prove, this is probably is the one you need to know how to prove here. All right. So I'm going to show you how to prove here because it's important proof here. So this is the what? So this is the sigma squares, right? So sigma square, we know is the second moment of what? About the means, right? So it's a second moment. So it's the expected value of x minus mu to the second moment, right? So it's the square. And now, okay, so let's see here. So I FOILed this. So this will be equal to x squared minus 2 mu x plus mu squares, right? Using algebra equation, I can FOIL it. Then I can divide this into the three terms here. This is x squared minus e. This is 2 mu x plus e to the what? Mu squares, right? And now mu is the means, right? So the mu really is what? It's a constant, right? So this is a constant. So as we show in the expected value before, so this will be the e to the what? X squared. And because 2 mu is a constant, I can take it outside the expected value, then this is ex. Also remember in the review, if you take the expected value of constants, what will be? Will just be itself. Okay, so now let's take a look. So what is these terms here? What is these terms here? This is the expected value of x squared. So what is this? This is the second moment about the origins, right? So second moment, I put a 2 here. About the origin, I put a prime. Okay, so then minus 2 mu. So what is this one here? This is expected value of the mean. That means it's the first moment about the origins, right? So we always use the mu to represent it, then plus mu square. So this is the mu2 prime minus this is 2 mu square plus mu square. So that's how do you get a 2 mu prime minus mu square. It's a very simple proof, but I think that's a lot of, your teacher might want you to prove it, all right? So the next series here, if the proof is not hard, but I'm not going to talk about it here. And so, but I want to make sure you understand the key concept here. The key concept here is if you add variances, right, add a constant, then this constant doesn't come. The variation is not going to change. Think about it, right? So I always use the example. I said, okay, this semester, like a freshman, right? So X is the weight of the freshman, right? Okay, so you have a weight here, different students have a different weights here. So after 1 year, all often, let's assume all often again, the freshman 15. So what happens here? So everybody gain the freshman 15. So basically, it's just the total, the average weight going to shift, but how about the variation among the different students' weight? Not going to change, right? So that's why when you add a constants here, it doesn't matter, right? So we're not affecting your variances here. So that is a very important, information also, right? It's not going to affecting that. And then if you times the constants here, right? So you times constants here, make sure you square the constants in the variances here. Like I say, some professor, they might want you to prove this one. So the way to prove this one, like I said, I'm not going to prove here. So you can do the same ways here. So this is a variance, ax plus b's, right? So you can do the same way, like a mu2 prime. That means expected value. That means what? This is what? That is the second moment to the means, right? So then the first things you want to see, what is the ax plus b's, right? So this will be a mu plus b. So the second moment, so this will be ax plus b minus what? Au plus b, right? And then this is the what? The squares, right? Okay. So now that's what is x minus mu to the square. And then you FOIL it, and then you use expected value. You should get this, these ones here. So I will encourage you try to prove this by yourself to see you know how to prove it. And then it's just like some algebra. So you need to, so in here you can see why the a disappear, right? So because this is ax plus b minus au minus b. So that's why, right? So that's why the b disappears, right? And then I almost solved it. So well, let's just try to finish. So just in case you have trouble, right? So here, this will be the ax minus au, the second moment, right? So what happened here? The a square, what can you do? Hey, take it out, right? So this will be the e, the a square x minus mu square. Then you can take the constants out. This is x minus mu to square. So what is x minus mu? It's sigma. So it's a square sigma square. So I say I'm not going to do it, but I still did the proof. So because I think this two probably, if your professor wants to prove something in these sections, these two are probably the most important formulas, and it's not too hard to prove. Okay, so now let's take a look at the example right now. All right, so now in here, don't forget, like I said, the hardest one is the notation. Okay, so now they want to find the mu2 prime, and the sigma for the random variable has the probability density functions f of x equal to the 1/2 and x equal to -2 and -1. So basically, they tell you this is my random variables, right? So the value of the random variable could be -2 and 2. And what is the probability? 1/2, 1/2. Okay, so let's take a look and see we still remember. What is the mu? Okay, mu is what? So mu is the expected value of x is the first moment, right? So it's the first moment about the origin, but we don't put a prime here. Okay, so now let's see here. That means you use each value times the probability, then add that. So what do you get here? The mu is equal to 0, right? Okay, now let's take a look at the next notation. Like I say, if you remember the notation, then you should be fine. It's just a notation sometimes a little bit confusing here. So this is a mu2 prime. If you see a prime, that means the second moment about the origin. So what is the second moment about the origin here? Will just be the x squared. All right. So based on the expected value, what is x squared? You square each terms, right? So it's -2, you square, then you times the probability, then plus 2, you square times the probability, right? So it's 4 times 1/2 plus 4 times 1/2. So what is here is 4 here. Okay, so now they want to find what next here, sigma square. Okay, so remember the sigma square is what is u2 prime minus u squares, right? So it's the second moment of origin minus the mean. So this is the 4 minus 0 to the square. So the sigma square equal to what? Equal to 4. All right, so it's pretty easy, right? Okay, as long as you don't get confused with the notations here. Okay, let's take a look at the next ones here. So next one is a calculate the variance of the random variable. X represent the number of the points when you roll a balanced die here. I'm trying to find the variance of X here. The X is the rolling a balanced die here. So this is X, this is f of X. So a balanced die, what do you have here? You have 1, 2, 3, 4, 5, 6, right? Because it's a balanced die, so what is the probability is 1,616,1,616,1,616. Good. Okay, so the variances, right? So immediately you say, okay, variance is going to be the second moment about the origin minus the mu to the square. Okay, so mu is expected value of x, right? So it's 1 times 1/6 plus 2 times 1/6 plus 3 times 1/6 and the to the 6 times 1/6. So if you get it, so if you add it, all going to be 7/2, so it's 3.5. So the mean is 3.5. Now I'm going to find the second moment about the origin. So what is the second moment about the origin? Is x squared, right? So what is x squared mean? That means 1u squared times 1/6 plus 2u squared times 1/6 plus 3u squared times 1/6 and plus 6u squared times 1/6 and I get it is 91/6. All right, so now you can say the sigma variance is equal to second moment about the origin, so it's 91/6 minus the mean square, so minus 3.5 square. And my answers here I got is 35/12. That will be the variances here. Okay, so remember that, right? Okay, so now the number 3 is here. This is a continuous because they give us the densities here. So I'm going to find what here? I'm going to find the same thing. The first moment, the second moment, and the sigmas here, right? All right, let's take a look at the first moment. So it's kind of like as long as you get not confused with the notation. So mu is equal to the EX. So what's that mean? Okay, so you said x times the PDF, right? So that's the x. So then you do a 0 to 2 and the dx, correct? Okay, so this one's here will just be the 0 to 2. So this is 2 the x squared dx. And I assume everybody know how to do the integration. So x squared is 3 and x cubed, and then this is 0 to 2. So you substitute the upper bound minus you substitute the lower bound, so you get a 4/3. Okay, so now let's do other ones here, right? So that's what is this notation again? So it's a second moment about the origins, right? So this is e to the x squared. Okay, so now that will be the 0 to 2. Now the x squared times the PDF is x/2 dx. So this will be 0/2 to the x cubed dx, right? So you integrate this one, is pretty simple. It's 1/2. X cubed is 4, the x fourths, correct? Then you put the upper bound and the lower bound. So you plug in the upper bound minus you plug in the lower bound. So you get a 2. So after that, so then you know your sigma square is equal to what? Second moment of the origin minus the first moment of the origin and square it, correct? And so that's why I have 2/9. Okay, that's it. All right. So these 3 problems let you get familiar with the notation and the most important couple moments, right? So first moment, the second moment, those are the moments we're going to use a lot. Then the next video we're going to introduce, we already see the graphs here. So like I think we already see the graphs. Where is my graphs? Oh, we already see the graphs here about the role the variance plays, right? So the Chebyshev inequality or Chebyshev theory is going to combine the variance and the mean. They will say, hey, what is the probability you will get within this variation from your data here? All right, so that's what we're going to talk about in the second video about the moment. So right now, we know how to find the first moment, we know how to find the second moment, right? So the Chebyshev inequality will give you an idea. So if you want to say what is the the probability from the mean plus or minus 2 sigmas, something like that, then what is the probability, how to find it. And that is what we're going to do in the second video. Then the last video, we're going to talk about one very, very important function. We call it moment generating functions here. Okay, and that's it. So these are the 3 problems. So we are kind of try to practice and get familiar with the different moment notations here. Okay, so that's it. And I'm going to stop here, and we are going to talk about more on our next video. So you have a good day, and so nice to talk to you, and looking forward to talk to you in the next topics here. Okay, bye.